Alright, so let's consider the potential energy for a spring. So over here we have this setup. So over here at point C, this is the undeformed position of the spring. This is the mean position. And at point B, we have the spring which is stretched. And at point A, we have the spring which is compressed. Okay, so now we can write F is equal to minus kx, where F is the force of the spring. So of course, when x is positive, the force is negative, that is in the minus x direction, that's towards the mean position. And of course, when x is negative, that is when we have at this position, force is in the positive x direction, so that's again towards the mean position, right? So let's find out the work done by this force. That would be Fs ds vector from point A to B. Yeah, that would be minus kx I cap dot dx I cap plus dyj cap integral from A to B. Of course, that would be minus kx dx integral from A to B, and that would be half kx a square minus half kx b square. So now of course we know that work done by the conservative force is a negative of the potential energy function. So from this we have half kx a square minus half kx b square is equal to minus delta u, implies delta u is equal to half kx b square minus half kx a square. What that means is that we can consider this as the ux function. So we have ux for a spring as half kx square. So that's the potential energy for a spring. Okay, so now let's discuss polar coordinates. So we have this setup, and any point P is described by the distance it makes from the origin and the angle it makes from the horizontal. So that's r comma theta is the coordinate system. And we have over here the unit vectors. We have radial unit vector, that's er cap. It's always pointing in the radial direction, and of course it changes as the point P moves. And we have e theta cap, always perpendicular and anti-clockwise from er cap. Now as the point P moves slightly, it of course increases from, let's say it goes from point P to point P dash. So this is the change in the radial direction, and this is the change in the theta direction. So we have this point P as r comma theta, and we have point P as r plus dr comma theta plus d theta. Okay, so let's now discuss the force in this setup. Let's now again consider the general case. Let's say the point moves along this line AB, right? We have this origin, and we consider the point P, and the force is, let's say, in this direction. So we have the radial component of force always in the radial direction away from the origin, that's Fr, and we have a transverse direction of the force, that's F theta. We have F vector is equal to Fr er cap plus F theta E theta cap, right? Similarly, we have this ds, right? So as this is ds vector, so this is equal to dr er cap plus r d theta E theta cap. Okay, so in order to calculate the work done dW as the point moves from P to P dash by an infinitesimal distance, we have dW is equal to F vector dot ds vector, that would be Fr Er cap plus F theta E theta cap dot dr Er cap plus d theta E theta cap. That would of course be Fr dr plus F theta d theta. Alright, so as the point P moves by an infinitesimal distance ds in the r theta coordinate system, we have a change in dr and a change in theta, that's in d theta, right? So this is ds. Of course, ds is equal to dr er cap plus r d theta d theta cap. Now let's consider a central force. Okay, so what a central force is, let's say if we have this kind of a setup where we have a spring to which it is attached a body of mass m. We have the gravity force which is in the plane of the paper, meaning that the only force that acting is in this setup is the spring force and there is no other force. Okay, so now in this kind of a setup, uh, the the spring force is always pointing towards the origin. That's the origin over here. So therefore, this kind of a force is called as a central force. Okay. Okay, so we would have the spring force in this case as K times R minus R naught. That's the initial position is R naught, and we would have minus ER cap because it's pointing towards the origin. Okay, this will be minus K R minus R naught. To get the work, that would be dW is equal to Fs dot ds. This would be minus K R minus R naught times dr, because of course er cap dot e theta cap is equal to 0. So then we have the work of the force itself. We integrate that, minus k r minus r naught dr from r is equal to ra to r is equal to rb, right? Of course, let's say the spring initially is at ra, and later on it is at rb. Okay, so then we have minus k r minus r naught square by 2 ra to rb, which is k by 2 ra minus r naught square minus k by 2 rb minus r naught square. Now of course we should write this as k by 2 ra dash square minus k by 2 rb dash square, where ra dash is the distance of the point A from the mean position. So what this ur half kr square means is that, let's say if we have this spring, and at this point when the body is at Ra, the value of potential energy is half k Ra square, and when it is at a different position Rb, the value is half k Rb square, and the work done from A to B simply minus delta U, that's half k RV square minus half k RA square negative of that, right? So it's only dependent on the initial and final positions in the polar coordinate system. It's independent of anything else. Therefore, the central force, is a conservative force. And yeah, let's conclude that. So how do we know if a force is a conservative force, right? So let's say if we have F as Fx I cap plus Fi j cap. If this equality holds where we have del Fx by del y is equal to del Fi by del x, this is sufficient condition to imply that this is a conservative force. Alright. Okay, let's also briefly discuss the unit of energy, or the same as the unit of work. So if a force F acts on an object such that this causes displacement of 1 meter and the force itself is 1 Newton, we say that 1 joule, Joule, joule is the amount of work performed by the force. Okay, so now let's look at the concept of power. Okay, so power is defined as the time rate at which work is delivered, right? So we have average power is equal to delta W by delta T. Okay, now as we approach the limit delta T tends to 0, delta W by delta T, we have dW by dt, that's the power. Now of course we know that dW is F vector dot dr vector, therefore power is F vector dot dr vector by dt, because that's F vector dot dr by dt vector, and that of course is F dot v. That's the expression for power. Okay, now let's look at another concept of mechanical efficiency of a machine. So we define that eta quantity as our output over our input. Now of course eta is always less than 1 because there is always some energy lost due to non-conservative forces such as friction, etc. Okay, so when we looked at the work energy theorem, we said the work of the non-conservative force is equal to the change in the mechanical energy of the system, right? So of course we considered that for a Newtonian frame of reference, right? But what if we have a frame of reference that does move with acceleration a? So say this frame of reference has got an acceleration a, and we consider a mass m on which we want to apply the work energy theorem. So what we do is we add a zero force to this mass, which is equal to negative of ma vector, where of course a vector is the acceleration of the frame of reference. So then we also consider the work of the zero force in the work energy theorem. So we write W of the zero force, work of the zero force plus the work of the non-conservative force is equal to the change in the mechanical energy of the system. So there we have it, the expression for the work energy theorem in the case of a Newtonian or in a non-Newtonian frame of reference.